Our next law deals with temperature and volume, Charel's law. The Boyle's law we dealt with pressure and volume. Charel's law deals with temperature and volume. And you might call it Charles' law in Michigan, but the rest of the world we pronounce as Charel's. There's Mr. Charel. He came up with this cool law. Pressure is constant. As the temperature of an enclosed gas increases, if we increase the temperature, the volume will increase. We're going to increase the temperature, the volume should increase, because as we increase the temperature, the kinetic energy moves around. Those molecules have a lot more kinetic energy. They're moving around, they're banging into each other, they're banging into the sides, they're increasing the volume if we have the same pressure. And we can see this on this graph here. As we increase the temperature in Kelvin, the volume will increase. It's just spreading out. Just think of a balloon. If you're heating a balloon, we're going to increase the volume. It's going to get bigger. That's how a hot air balloon works. Hot air balloon increases the volume. We increase the temperature. You got the little fire going down. We increase the temperature. It increases the volume. That volume is less dense than the air outside, so since it's less dense, it's going to float. So this fluid inside, because it's hot, it's going to be moving around a lot, increasing the volume. When it increases the volume, it gets less dense, thus it's going to float. Here's another awesome graphic of Charel's law, temperature and volume. Look at this. We're keeping on the lower left, we're keeping the pressure constant at 1.5 atmospheres, but the temperature we're increasing, and as we increase the temperature, those molecules inside that piston are moving up. They're expanding, because we're not forcing that volume to be the same volume. It's expanding because of the kinetic energy. This is also another cool graphic that I can just stare at for hours, and I will get it for you. A lot of people have asked me, hey, Mr. B, can I get this? My birthday's coming up. This is what I really want. I don't want a new car. Yeah, I'm turning 16. I want some of these graphics. I'm going to say, yeah, no problem. And here's the equations. We can write it in different ways, as you can always write algebraic equations in many different ways. V1 over T1 equals V2 over T2. V2 over V1, T1 equals over T1, T2 over T1, V1 T2, V2 over T1. And you might say, hey, which one do I remember? How can I keep track of all these? Well, I'll show you when we go over the combined gas law. Really, you just have to memorize the combined gas law, and it takes care of all of these laws. Let's look at an example here of Charel's law. Gas has a volume of 10 liters, so let's just write that down. Volume 1 is 10 liters, 200 degrees Celsius. So temperature 1 is 200 degrees Celsius, but we cannot leave it in Celsius. We have to change it to Kelvin. The way we change it to Kelvin is add 273, so we have 473 degree Kelvin, or really 473 Kelvin. V2, we want to know what it will be. We don't know. If the temperature of T2 is 20 degrees Celsius, which is 293 Kelvin. So let's look at this equation. We have V1 over T1 equals V2 over T2. And we're solving for V2. So that just means we can rearrange this equation to be, and now we just plug it in. We have 473 times 10 divided by 293. That equals 16.1 liters. So you can see it expanded quite a bit there by 6 liters. Okay, let's look at Gay-Lussac's law. He deals with pressure and temperature. There's Mr. Gay-Lussac. He said if a volume is constant, so we have the same volume, as the temperature of a gas increases, the pressure will increase. That makes sense as well. If you throw a aerosol can in the fireplace, the pressure is going to go up. That kinetic energy is going to increase. Molecules are going to be moving around like crazy, bashing against that enclosure, and it's going to increase that pressure dramatically. Here's a cool little GIF. I know we have Charles' law on the side there. Also, we can look at Gay-Lussac. On the left here, where it says Charles' law, the temperature is decreased and the pressure will also decrease there. And if you look on the right, as the pressure of this tire goes down, the temperature will go down. Now, if you drive a car, and sometimes the cars will have the tire sensors that will tell you if the pressure is too low. Now on cold days, the pressure might be much less, or will be less, in those tires because the molecules are moving around, the air molecules in those tires are moving around much slower, they're compressing, they're getting closer together, so the pressure is going to go down. So in the winter, my car will tell me that the pressure inside the tires, they're much less than they would be on a hot day. On a hot day, the molecules are going to be moving around more and it's going to be much higher pressure. Here's his formula. P1 over T1 equals P2 over T2, or P1 T2 equals P2 T1. Either way, again, once we get to the combined gas law, it takes care of it all. Let's try a problem here. A gas has a pressure of 10 kilopascals, so pressure 1 is 10 kPa. Temperature 1 is 10 degrees Celsius, that equals 283 Kelvin. Pressure 2, we don't know, but temperature 2 is 100 degrees Celsius, which is 373 Kelvin. So we have P1 over T1 equals P2 over T2. And so we're solving for P2, so we have T2 T1 times P1 equals P2. 373 multiplied by 10, all divided by 283. That equals 13.2 liters. So we can see as the temperature went up, so did the volume. Now, the next one is the combined gas law, and allows you to do the calculations for a situation in which only the amount of gas is constant. So the pressure, the volume, the temperature, they can all change. So we have P1 V1 over T1 equals P2 V2 over T2. So we might have all three of those variables change, which of course can happen. Now, I don't have a scientist to show you by the name of combined. The reason it's called combined is we combine those gas laws. It's not named after a person named combined. Now here's a combined gas law problem. What you want to do is just write down what you're given, and what you tell by is the units usually, and of course they might tell you, but not always. Write down what you're given and then what you want. So pressure 1 is 200 kPa, volume 1 is 20 liters, and temperature of 200 K, so it's nice it's in Kelvin already, but it's not very difficult to change it into Kelvin from Celsius. 200 K. Then I raise the pressure to 14 kPa, so pressure 2 is 1400 kPa, and increase the temperature to 300 Kelvin. Wow, what's that going to do to the volume? That's what we want to know. So let's use our combined gas law equation. P1 V1 over T1 equals P2 V2 over T2. And we can just start plugging in. And well, first, I personally like to solve right away for T1. And so we rearrange this. We can flip both sides to get, I'm sorry, we're solving for V2. We don't have to flip both sides. So we're solving for V2. So that just equals T2 times V1 P1 So we're just using some of our algebra skills, and now we just plug in. We fill this in, those cancel out, those zeros cancel out, so it's 6 divided by 14, which equals 0.4 liters. Even though we raised the temperature, the fact that we increased the pressure so much had precedent because there was more of a factor there, and we decreased that volume. That's using the combined gas law. We have all these different variables changing. We just plug things in and there we go. What I was talking about before is we can do any of those previous problems using the combined gas law. For instance, here we have a man heats a balloon in the oven. Don't know why, but he does. If the balloon initially has a volume of 0.4 liters and a temperature of 300 K, what will the volume of the balloon be after he heats it to a temperature of 400 K? So we might not. So first thing, just write this down. Volume 1 equals 0.4 liters. Temperature 1 equals 300 K. We want to know what volume 2 will be and what temperature 2 is 400 K. Now we might not recognize this as being Charel's law, or Charles. And it doesn't, we might say, gee, what is V1 T1 over T1, or is it T1 V1? It doesn't matter. If we remember what P1 V1 over T1 equals, that's just P2 V2 over T2. That's a combined gas law. All we have to do is plug in. Now you say, what about pressure? Well, in this case, pressure is constant, so pressure means when something is constant, it just stays the same. So those will just cancel out. And then we can just we just get rid of that, and we can just say, oh, here we go. So if we're ever trying to remember what those laws are, use the combined gas law, and whatever's constant, just erase. Those just cancel out. Now we can just plug in. We're solving for V2, so this goes over here, T2 V1 over T1, that is 0.4 times 300, times 400 over 300, that comes out to be 0.5 liters, so half a liter. Let's look at another example where we can use the combined gas law. If we have 1 liter of gas, just write this down. So that's volume 1 equals 1.00 liters. Standard STP compressed to 473. So that's V2 equals 473 milliliters. But we cannot keep it in milliliters. We have to move it to liters. So that's 0.473 liters. What is the new pressure of the gas? Well, we have to say, well, what is the pressure? What is the first pressure? Well, the first pressure, it's at STP, so that's 101.3 kilopascals, and we want to know what P2 is. Gee, how did that equation go? This is Boyle's law, but I don't remember. But let's use the ideal gas law. P1 or V1 over T1 equals P2 V2 over T2. So the temperature did not change. So the temperature is constant. You can get rid of it. And now we have just Boyle's law here. And we can just say a 101.3 multiplied by 1 equals P2 multiplied by a 0.473. Well, we're going to have to divide by 0.473. Usually I like to do these before I plug in numbers. So that's just 101.3 divided by 0.473, 214 kilopascals. The pressure went up quite a bit. It doubled basically because we halved the volume more or less. So these are just examples of where we can just do any of those problems, Charel's, Boyle, Gay-Lussac, just by using the combined gas law. Fun stuff.